Hello, myself Dr. Anuj Purwar. Today I am taking lecture on sources and collection of water part 1. Sources of water supply. The sources of water supply may be divided into following two classes according to the source and the method of collection. First is the surface water and second is the groundwater. Surface water. The rainwater collected comes under the surface water, water from the rivers, water from the natural lakes, and water impounding reservoirs it under the surface water. In groundwater sources, water from the springs, water from shallow wells, water from the deep and artesian wells, and water from the horizontal galleries. Selection of water sources. In selecting a particular source of water, following important points are generally considered. First is the quantity available. The quantity of water available from the source must be sufficient to meet the various demands during the entire design period of the scheme. The quality available. The water available from the source must not be toxic, poisonous, or injurious to the health. The impurities present should be such as to be removed easily and economically by standard treatment method. Distance of the source. This is one of the important factors. The source of water should be situated as near the city or town as possible. When the distance between source and city is lesser, length of pipe conduits are required. Topography of the intervening area. The area of or land between the source and the city should not be quite uneven. It should not contain deep valleys and high mountains. In case of such uneven topography, the cost of carrying water pipes will be enormous. Elevation of the source of supply. The source of water must be on a high contour, lying sufficiently higher than the city so as to make the gravity flow possible. When water is available at lower elevation than the average city level, pumping has to be restored with high installation and operational cost. Aspects of surface water. Influence of catchment area on water dusting. If the slopes are steep and rocky with little vegetation in the catchment area, the water may be expected to be quite clear. If the vegetation is in the sufficient density as to cause stagnation in the flow of the water, a colored water may be in result. Surface water impounded either naturally or artificially from areas under cultivation, generally carrying high turbidity. Impounded surface water sources. Water of lakes, ponds, and reservoirs may be categorized as impounded surface water. Impounded surface water shows less pollution because in relatively quiescent waters, solid matters excepting colloidal clays cannot remain in suspension, so they settle down. However, soluble pollution may cause greater effect due to the abstraction of oxygen for its mineralization, since the transport of oxygen to deeper layers is by water movement. Movement of impounded water. Horizontal water movement are of importance in early spring, when the surface layer of water is warmer than the lower layer because of the layer flowing out or in may be confined to a small volume of water in this higher layer, and any surface pollution entering at these times may be potent at greater distances because of this lack of dilution by colder, deeper, and larger volume of the water. Natural purification, the effects of the vegetation. Vegetation undergoes decay and adds an extra load on natural purification processes. Color may be added from leaching of vegetable tannins and the subsequent oxidation of these substances to compounds of dark brown color. Removal of vegetation as much as possible is advised. Odor in surface water. Odor in surface water supplies are mostly due to microscopic plants and animal life. Odor may be due to presence of volatile oils in the cells of these planktons, and the odor of some is so intense that it can be detected when present only in one part in several million part of the water. Water rich in uroglanopsis are said to be have an odor similar to cod liver oil, while the odor of cyanura is described as spicy. Self purification of steam. Most of the flowing water undergoes a degree of self purification after the introduction of waste, whether it be soil drainage or sewages that produced by the industries. The rate of purification depends upon the nature and amount of matter added, as well as the rate of flow, velocity of the flow, interaction of waste, rate of oxygenation, amount of sunlight, and many other chemical, physical, and biological characteristics. Dilution of flowing water. Dilution greatly decreases any pollution because pure water carries a quota of oxygen. Hence, dilution adds oxygen for the oxidation of the pollutional materials. Stream water freshly polluted by sewage may contain as high as 1 crore organisms per milliliter when dilution is small, but with increase in dilution of the sewage by stormwater and within a short period the number may reduce a great extent. The mixing of two water of different chemical characters frequently promotes sedimentation process. Chemical purification of flowing water. An outstanding example of chemical purification occurs in water charged with iron salt and acid. Such water in flowing over limestone are neutralized or precipitated with definite improvement in the water quality. Here the iron salt available, acid is available, and this reacted on with the limestone and the precipitation is happen, so this pollutional chemical can be removed. Effect of sunlight on stream purification. Direct sunlight has a germicidal effect upon many bacteria. The stimulation of green plant growth by sunlight adds oxygen which becomes available for waste oxidation. Now, storage reservoirs. A water supply scheme drawing water from river, natural ponds, or lakes may fail to satisfy the consumer demands during low flows. A barrier in the form of a dam in most of the cases is constructed across the river or stream so that a pool of water is formed on the upstream side of the barrier. This pool or artificial lake formed on the upstream side of the dam or barrier is known as storage reservoir. The quality of this reservoir water is at most similar to that of a naturally. So here is the picture. Here is the dam section is shown. Left side of this dam section, here is the reservoir, storage reservoir, and right direction the minimum head required for the power generation. So here the upper limit, which is known as the during the flood maximum water is available. Then normal water level, which is available in most of the time, and the minimum pool level. Then there is the dead storage level also shown in this figure. Here we will discuss some important headings regarding this storage in the reservoir. So first is maximum pool level. What is the maximum pool level? During high floods, water is discharged through dams over spillways. Still there is rise in water level in the reservoir above normal pool level. The maximum level to which water rises during worst design flood is known as the maximum pool level. Normal pool level. The maximum elevation to which the reservoir water surface will stand during normal operating conditions. Minimum pool level. The lowest water elevation in a reservoir which has to be kept under normal operating conditions. This level is fixed by the elevation of lowest outlet in the dam, which guides minimum head required for functioning of turbines for power generation. Useful storage. The volume of water is stored in the reservoir between the minimum pool level and the normal pool level. This is the useful storage. Dead storage. Water is stored in the reservoir below the minimum pool level is known as the dead storage. Surcharge storage. The volume of water is stored between the normal pool level and the maximum pool level. This is known as the surcharge storage. Valley storage. Before construction of the dam, some variable amount of water is stored in the stream channel, and this is known as the valley storage. Reservoir yield. The amount of water that can be drawn from the reservoir in any specified time interval is known as reservoir yield. Reservoir yield depends on inflow into the reservoir and the reservoir losses, which may be due to the leakage through the embankments and through the evaporation. Capacity of reservoir. After the reservoir is filled, water is drawn from the storage. Drawing of water from reservoir, this is known as the draft. The amount of storage is a function of the expected demand. Hence, reservoir function is based on redistribution of inflow with respect to the time for satisfying the demand. Methods of estimate capacity of the reservoir. Here the following method. First is graphical method. This is also known as the Ripple method. This is graphical inspection of the entire record of historical stream flow for a critical period. It is valid only when sigma D less than is equal to sigma S. D means demand as for the supply during the period of the record, and works well when releases are constant. It provides storage requirement by evaluating sigma in bracket S minus D. Slope of the mass curve give value of the inflow S at that time. Slope of demand curve gives the demand rate D or yield. The difference between the lines A plus B tangent to the demand line sigma D drawn at the highest and lowest point A and B respectively of mass curve sigma L give the rate of withdrawal from reservoir during that critical period. So here the picture we are seeing. So first there is a graph showing the supply and demand curve. Demand is constant if always, and supply is like that fluctuated with the time. And in second figure there is a cumulative supply and cumulative demand is shown, and as we have discussed, we draw the tangent as the point A, capital A, and as well as the point as capital B, and calculate the value of A, small a, and small b in comparison to the mass demand. And so as adding these value, we get the A plus the summation of the A and plus B. Analytical method. Thomas and Fearing develop a procedure for determining the minimum storage capacity of a reservoir based upon two needed cycles. The procedure is based on the assumption that the reservoir, if full at the beginning of the dry period. Monthly runoff is denoted as small h and the monthly draft or demand as the capital D. So deficiency for each value D minus H is obtained. Cumulative deficiency as D minus H is calculated by cumulating at the start of maximum dry period. The required maximum storage is highest numerical value in as this is in bracket D minus H. Values or the maximum cumulative deficiency at the end of the dry period. So here we will see the example based on these two methods. With the help of mass curve, find out the required storage capacity of a reservoir for the following given data. The draft is uniform with 18 million liter per month. The runoff is given in millions liter per month. So month is given for the data is given for the 16 month and corresponding runoff are given in that example. So in solution, in column first we put the month, in second as runoff, and in third column we will calculate the cumulative runoff. As for 1 month, runoff is 24 in value. In second month, this is the 24 plus runoff in second month, this is 22. So total cumulative runoff is 46. So in similar way we will calculate the value for remaining month. And cumulative draft for 1 month 18, in second month this will be the 36, for the total third month this will total the 54. So this is we will calculate the cumulative value in similar way. On basis of these we will draw a graph against the time in month to the cumulative runoff or the draft. So demand line in that case is a constant line. This is we are showing as shown in this graph, and we will get the cumulative runoff. Draw the cumulative runoff curve line. This is then a curve shape, and here we will calculate the maximum vertical intercept after drawing the tangential line at the point C as well as the point D, and in similar way at point the B we will do the same thing and calculate the value B dash and D dash. We have done the all discussed all the detail. A graph has been drawn between cumulative runoffs and times in month on y-axis and x-axis respectively. Then again same graph curve between time and cumulative draft. Cumulative demand or demand has also been drawn. So this is the straight line. So now required storage capacity of the reservoir is the maximum of the vertical intercepted ordinate between the two tangents drawn to a peak and a true consecutively. In figure, d dash is the maximum vertical intercepted ordinance. So storage capacity is equal to length of the line d dash into scale. What is the scale? In what scale we have draw this graph. So this is value is 0.8 centimeter and scale is 25. So we got the answer. Storage capacity is equal to 20 million liters. Example second, calculate the required storage capacity of a reservoir for the following condition. The draft is uniform with 18 million liter per month. This is the same example, but now we will calculate this example by the analytical method. So in this method, first column we kept the month, in second column this is the runoff, and third column this is the as well draft. Draft is constant, so in every column, in whole column their draft is the 18 million liter. So we will calculate the D minus Q, and then we calculate the cumulative value of the D minus Q in column 5. So all these calculation as shown in figure, here also we put all these values here. So now the calculation. The runoff and draft values as given in table above are in million liters. As explained earlier, surplus negative and deficiency is the equal to the positive. And column 1, 2, 3, the given data have been all entered. Further, column 4 is equal to column 3 minus column 2. Now identify the dry period, which is the period of deficiency. This is the all positive values. Sum of the positive values in each dry period is equal to 16 million liter and 18 million liter. Highest numerical value among the sum of the dry period is maximum. This is the 18 million liter. Now we will talk about the column 5. Start cumulating of the column 4 at the beginning of the maximum dry period. Maximum required storage is the maximum positive numerical value of column 5. This is the 24 million liter. So in this way we can get the answer. Source and collection of water, part 1. In next lecture we will discuss about the sources and collection of water, part 2. Thank you.